So you could turn it in early if you want to, that's fine. But it's now due on Monday, April 14th, so I'll give you an extra week for that. And then there's a homework on the regression due next week on Wednesday. So then today we're starting the section on graph analysis and kind of social network analysis and kind of these sorts of topics. And so today we're going to be talking about a more general technique, and we're actually going to have mainly lots of definitions and examples. And this is going to be about Markov chains. The reason to spend a lecture on this is because the following lecture next week, Monday, we'll be talking about the PageRank algorithm, which is this hugely influential algorithm. This is kind of how Google got started by kind of, they invented this algorithm for understanding the structure and the importance of web pages on the web. And to really understand it, you need to understand Markov chains. So we're going to spend a lecture doing this. I think for a really global analysis of graphs, there are two really important conceptual tools. One of them was using like the eigenvector structure and the Laplacian structure, and we talked about that a bit in the graph clustering, in the spectral clustering lecture. The other really important thing, I believe, is to understand graphs is Markov chains. So we'll be talking about this. There's some other cool things we'll talk about later after we kind of wrap up a series of lectures on PageRank and how you do it at large scale, and this gets into things like MapReduce. So in addition to just the basic ideas of Markov chains, we'll also talk about at the end a really cool algorithm. It's called the Metropolis algorithm, which is based on Markov chains in a certain way and is kind of critical for doing most of computational Bayesian analysis. So I'll just kind of describe it. I won't be able to get into the Bayesian analysis part of it, but it's a really cool tool and has some interesting history to it. All right, so Markov chains. All right, so who's heard of a Markov chain before? Okay, good. So who's not heard of one? Okay, so most people have heard of them. So when I was an undergrad and a grad student, I was taught Markov chains in classes several different times, and I think I kind of learned something new each time. So hopefully you'll still get some interesting stuff out of this lecture. So to kind of to kind of make this a little fun, I think there are three important kind of life lessons that really summarize on Markov chains. So I'll kind of write these up, and then we'll see how these come from. If you've seen Markov chains before, then maybe these will kind of make sense right away. So only your current position. Only your current position matters. Don't worry about the. Don't worry about the past. Okay. Okay. So. So just take one step at a time. You will get there eventually, or you won't. Okay? And then everyone as perfect karma. Okay, so these are maybe abstract. These are, important things to keep in mind in life in general, also for Markov chains. So of those who know Markov chains, do all these kind of make sense already? Who thinks these all make sense? Why Markov chains teach you this? Okay. Okay, well, good. Okay, so hopefully you'll understand this by the by the end of the class. Okay, so you can think of Markov chains more generally than just working on graphs, but we're going to be talking about them in the context of graphs. So just to review, I have this example graph I like to use. All right, so I'll keep this graph on the board. Just to review, the graph has these nodes, which I've written A through H here, and there are edges in between the nodes. And so, there are several ways you can think about these graphs. So instead of writing this all from the board, here it is from the notes. There's a way where you can just write down all the vertices and write down all the pairs with which are these edges. And this is the representation for this graph here, written up. I think I forgot H, but in the vertex set. But the second way you could think of a graph, which is going to be important, is to think of the graph as an adjacency matrix, right? So what we're going to do here is to have this matrix A, where the first column tells you, if you think of these as being in sort of order from A to H, the first column tells you the other nodes which A is connected to, right? So it's not connected, doesn't have an edge to itself, but it's connected to B, C, D, not E, not G, not F, and not H, right? And so that's the first column of this graph here, and you can think of filling out this as a big matrix. Okay, and then there's also this pictorially is this ball and stick line. Okay, so we're going to use this to be consistent. Here. Okay, so we're going to use this graph as an example. Okay, so we're going to think about these graphs. And so then, when you're dealing with the Markov chain, okay, so Markov chain will be defined based on three things: a vertex set, a probability transition matrix, and an initial state on Q0. So V is going to be a vertex set. So here, if you have a graph, it's the same vertices as the graph. So P is going to be a probability transition matrix. And so Q is going to be an initial state. All right. So this vertex set is very self-explanatory. I'll spend some time on this probability transition matrix. It's easiest to understand this initial state and the idea of a state, right? So if I have a state Q, I'm going to think of this as a vector. And so if I have a vector, it's going to have the property that each q of I, so each entry is going to be greater or equal to 0, and that the sum over I of all these entries is going to be exactly equal to 1. Okay, so if I have an initial vector, or a vector that looks like this, so this is a valid state, and this says, because I have a 1 here and a 0 elsewhere, the probability of being in state B, which is the second state in my list here, is 1. So probability 1 of being in state B, probability 0 of being in any other state. I can instead have a different state that has values 1 over 10, 0, 0, say 3 over 10, 0, 6 over 10, and 0. Okay, so here I have, these are all greater or equal than 0, and they all add up to 1. This is saying with probability 1/10, I'm in state 1, or I'm in state A. With probability 3/10, I'm in state D. With probability 6/10, I'm in state F. Okay, so in our example, we use this one as Q0, but it could be distributed in these different ways. Okay. And then this probability transition matrix is going to somehow describe how things move in this Markov chain. Okay, so we have a state. This describes the probability of being someplace, and the chain is something that is kind of moving around the graph. So I start out, I know I'm in state B, and this P is going to tell me how I'm going to move to these other different places in the graph. Okay, so this is going to be a big matrix, and it's going to be derivative of, typically, of the adjacency matrix in the graph, right? So I have this adjacency matrix, and given this, this will allow me to define this probability transition matrix. And so if I look at the first column, it's going to be 1, 0, 1/3, 1/3, 0, 0. So I'm going to take each of the columns here, and I'm going to normalize them so that so I'm going to divide through by the total number of entries so that the sum of the columns is equal to 1. Okay? And so if I did this for this adjacency matrix, I'm going to get probability transition matrix that looks like this. Right? So the first column is 0, 1/3, 1/3, 1/3. The second one is 1/2, 0, 0, 1/2, 0. Okay, so and you can read the rest off of there. So what's going on is this is saying that if I'm in state B, okay, then I'm going to look at the second column here, and I'm going to say, this tells me where I might transition to. So if I'm in this position in the graph, so Q0 says I'm in state B, then I can only move to two different places, and it depends on the edges of the graph. So I can move to A or I can move to D, and they're both, and both these are equally likely, right? So this first one corresponds with the edge let's see, from BA. Okay, so in general, I'm talking about this graph is going to be undirected, but more generally, you can have directed edges on the graph. So you can have going from H to F. And we'll talk about some of these later. So if this edge was directed, then this would be an ordered pair from B to A, and this is the ordered edge from B to D. Right, so the first one is from B to A with probability 1/2. This was from B to D with probability 1/2. Okay, so it's saying if I start out in state B, I'm going to transition to another state after one step. and I'm going to end up in either A or D with equal likelihood. Okay, and so B corresponds to this second column is the one that corresponds with state B. Okay, so this is how you define the probability on transition matrix. And now that I have these elements, I can start to do some cool things, right? So if I start out with Q0 being here, then I can say that state Q1 is the probability transition matrix times Q0. So I can take my state represented as a vector of probabilities of where I might be, and I just multiply it by this matrix, and I end up getting the state Q1. Okay, so let's see what happens when I do that. I'm in B, then Q1 is going to be equal to 1/2 the time I'm going to be in A, and 1/2 the time I'm going to be in D. And that's because I had a 1 here, and you multiply by this matrix, basically the 1 gets multiplied here, and then gets pushed over this way. Right, so you can think of this matrix P and this vector Q transpose, and so it gets pushed like this, and this gets you, so if this was Qi, this would be Qi plus 1, right? So this is state Q1 after Q0. I can also write that Q2 is going to be equal to P times Q1, which is equal to, based on the definition of Q1, this is P times Q0. You can also write this as P squared times Q0. So you can do kind of a matrix, power of a matrix. And so then if I write out Q2, and I'll use this one up here on the overhead projector. So I started out with 1/2 probability being in A, 1/2 being in D, and now I need to look at where I can move from both of these, from both of these states, right? So 1/2 the time I start out in A, and so I'm going to get 1/3 going to B, 1/3 going to C, and 1/3 going to D. Right? So if I'm here, 1/3 the time I go back to B, 1/3 the time I go to D, and 1/3 the time I'm going to C. So you can note that the probability of along this edge, even though it's just a single edge here, it's not the same going in both directions. So I'm going to get, so Q2 is going to get 1/3, is in A, 0, 1/3, 1/3, 1/3, 0, 0, 0, 0. But this was times 1/2. This was coming from state A. So this is 1/6, 1/6, 1/6. Right? But I could have also come, half the time I also started out in state Q1 being in location D, which is up here, and from there I could have gone to B with probability 1/3, to A with probability 1/3, and to C with probability 1/3. Okay, so I'm going back to A, so I'm getting 1/3 here, or so 1/6 here. So 1/6 of the time I'm going back to D, plus 1/6 of the time I'm going to C. I'm not going to D anymore, and D is good. So I'm adding these up, and so I get 1/6, 1/3, 1/3, 1/6, 0, 0, 0. Okay, and if I add up these values, it should add up to 1. 1/6 plus 1/3 plus 1/3 plus 1/6 is 1. So I have to be somewhere, right? So this tells me the probability of being in any of these states. So this is after. So one way of viewing this is I'm kind of randomly walking around this graph. I start out somewhere, and I'm jumping to one of these, other nodes along these edges. And so Q0 is where I am after 0 steps. Q1 is after 1 step, and Q2 is after 2 steps. Okay, so now no, could have never left this part of the graph so far. I'm only in these two parts, and 1/3 of the time I'm in C, 1/3 of the time I come back to B, and 1/6 of the time I'm in one of these A or D states. So that's what is encoded in this Q2 vector here. Okay, so that's what this is encoded. Okay, so if I can also write out that Q3, again, is P times Q2 equals P3 times Q0. And so this one is going to be, I'll just write out the answer. This will be illustrated in certain ways. Be 1/3, 1/9, 1/9, 1/3, 1/9, 0, 0. Okay, so after 3 steps, if I start at B, I can finally make it over to E. But it only happens 1/9 of the time. Okay, so now it makes sense if I get to E, I couldn't have made it there in 2 steps. I can't get there in less than 2 steps. I could get there in 3 steps, but only 1/9 of the time do I actually make it over here after 3 steps. So a small fraction of the time. Once I make it here, then I can start getting to these states as well, but it's more likely I'm still in this part of the graph. Okay, so note that I wrote this out as this matrix power to the 3rd. What this means is that if I wanted to, I could have just said after Q0, there's this single matrix P to the 3 that says, where might I be after 3 steps? I can just multiply it by this matrix, P cubed, and I automatically tell where I am after 3 steps. Right? So I can do that for any value. If I wanted to know state Qi for any value I do P to the I power times Q0, and this tells me where I would likely be after I steps. Okay, so so all this is called the a Markov chain, and the Markov is named after Andrei Markov, and more specifically after what's called a Markov process. And this is something that it's a process that you're running for a while, but what you're going to do next only depends on the current state that you're in. So if you're in a current state, it doesn't matter how you got to that state, it only matters where you are at that point in time. So it only matters where you are, or what your current state vector in order to get to the next state, right? So I can write in general, Qi is equal to this probability transition matrix times Qi, I'll call this Qi plus 1, is equal to the probability transition matrix times Qi. So the next state only depends on the current state. It doesn't matter where I was in Qi minus 1, or Qi 1, or even Q0. It only matters the current state. Okay, and so this is kind of what I mean by this first life lesson. Only your current position matters. Don't worry about the past. In order to understand how this works, you only need to care about what your current position is. So you don't have to worry about the whole history of how you got there. Okay, so before I get into this anymore, it's important to point out that there are really 2 ways of thinking about a Markov chain. Okay, so So there are two ways of thinking about this, and they're both used very importantly in different sorts of analysis. So the first way of thinking about it is that you're in one, let's say, you're at one node, or say one vertex at any time, and so P tells where you might go next. Okay, so this kind of corresponds, well, with the thinking here that Q0, I was definitely in state B. Okay, I was in state B to start here. And then when I do this probability transition matrix, I get this Q1 vector, says half the time I'm in state A, half the time I'm in state D. Okay, but this is a probability of where I might be. What I want to say is, I'm only going to be in A or D, but I'm not in both of them, right? So I'm kind of walking around this graph randomly. I started at B, and then I flipped a coin. If it was heads, I went to A. If it was tails, I went to D. And so I actually kind of think of moving something, and then I look at the probability transition matrix again, and I move to one of these three locations again. Okay, and so I actually only maintain the location of one state at a time. Okay, this is in contrast to the second way of thinking about it, where you kind of keep track of Q, which is a distribution of where you might be. So this is saying, I don't care which of the states I'm actually in when I do this random walk. But I want to keep track of where I might be and kind of see as this probability kind of spreads out. Right? So I started having, being in the state B, and then I could have been in state A or D, then I could have been in A, B, C, or D, then maybe I could have also been E. And this kind of, as I get this Q3, this is kind of the picture I was painting here, the second view. And these are different. So often when you're taught about this, you think of one of these views or the other. Okay, so this second view, and this actually corresponds to very different algorithmic ways of thinking and using these Markov chains. So the second view is what will be very useful for thinking of PageRank, which we'll talk about on Monday. This first view will be associated with what's often called the metropolis algorithm, and is used within, say, Bayesian analysis, but in lots of other things as well. So we'll come back and talk more about this view after I kind of finish up some definitions of what is a Markov chain. Okay, but these are, so often you're only introduced one of these two views, and I've talked to people who've learned one and then they get confused when you try and explain the other. So these are different ways of thinking about them, and you can get confused about them. But you're usually doing one of them or the other. Okay, but they're of course very related. So type 2 tells you the distribution of where the point is, but 1, you're actually only maintaining one of these possible locations at. Okay. All right, so we're doing good. So kind of explain basically what is a Markov chain at this point. Okay, so hopefully kind of following so far. But I need, in order to tell you interesting things about it, I actually need some more definitions first. Okay, so I warned you this class was going to be lots of definitions and examples. So let me quickly running out of board space here. So all right, so So we're going to have this property called ergodicity. Okay, so a lot of you have heard of Markov chains. So who's heard of the notion of a Markov chain being ergodic? Okay. All right. Well, it's only a few of you, so that's good. Okay. So, what this means is that if I look at this view where I'm saying that qi plus 1 is equal to qi, well, I can now also write this as qi plus 1 is equal to p times I plus 1. Actually, let's write this as n. Qn is equal to p to the power n times q0. Okay, so now we can define Qn, which is this probability distribution after n steps. Okay, and so so this says that there exists a t such that for all n greater or equal than t, that every entry of Pn is positive. Okay, so this is equivalent to saying that every entry of Qn is positive. Okay, so this is saying that it's not that after at a certain time t I could be in every state I have a chance of being in. It's stronger than that. It says that for all time afterwards, I always have a chance of being in every state. Okay, so I have a chance of being anywhere in the graph. Okay, so this Markov chain I've set up, as well as we'll see, has this property. This Markov chain is going to be ergodic. After, I think for t equals 7, I could potentially be in every one of the states. And I will always have a chance of being in one of the states afterwards. So this is what it means to be ergodic. And so to understand it, it's really clear to define what properties does a graph have if it's not ergodic. Okay? So if it's not ergodic, then it has one of 3 properties. Okay? So if it's not ergodic, it's either going to be cyclic, and I'll explain and give examples of each of these. It's going to have absorbing and transient states, or it's going to be not connected. Okay, so I'll go through examples of each of these. So if it's cyclic, and in fact, all we need to write this down is just the probability transition matrix. We'll see why the Q0 state is not going to be important in looking at whether it satisfies these properties. So if it's cyclic, then what this means is that there's some sort of cycle in the graph. Well, this graph has a cycle, but it's a cycle, and you're always kind of in this cycle. Okay, so an example of a cyclic graph is going to be, or of the probability transition matrix is going to be, just look like this. Okay, so this corresponds with a graph with just 2 nodes, A and B. And if I'm in A, I always go to B, and if I'm in B, I always go to A. Okay, so it doesn't satisfy this ergodicity property. Now, at some point in the future, there's always a chance, at some point in the future I'll be in A. There's always a chance at some point I'll be in B. But I'm only going to be, if I start in A, I'm only going to be in B on the odd numbered steps. And in every odd numbered step, I'll be in B. I could also, and then only be in A in the even numbered steps. So this needs to happen for all values of n greater than t. And there's no value of t for all values large run. I could be in each of the states. You know, it doesn't need to be a cycle of size 2. It can be a cycle of size 3, where C always goes to B, B always goes to A, and A always goes to C. This also works. And it doesn't need to be just 3 edges. You can have something where you have A and B, and you have C, D, E, and F. All right, let's simplify it. So A goes to one of these with 1/3 probability. B goes to one of these with 1/3 probability. C goes to A with 1/2 and B with 1/2. D always goes to A, and E always goes to B. This is also cyclic. If I start at A, I will be in, I will only be in A or B on the even number steps, and only be in C, D, or E on the odd number steps. I cannot be in the other on every other step.
So, if I understand correctly, ergosity means after, say, for n greater than or equal to t, the distribution cannot have any value as 0?
Or,
I mean, is 0 allowed value? Or
yeah,
not?
so 0 can't be allowed. That's actually a slightly stronger property, as we'll see with these things.
Okay.
So if you have a 0 probably being someplace as being 0, that's clearly bad.
Okay.
So that's bad, but it doesn't even have to be 0. It can be approaching 0. So there's some kind of limiting condition to inward, and I'll describe that here in a minute. Okay, so these absorbing and transient states are things where there are certain parts of the graph that you can wind up in, and then you can't get back to the original person. Okay, so let me start with a very simple example here. So let's say B and C go back and forth between each other. A can either go to itself, or it can go to B. Okay, so if I start at A, if I leave A, I can get to B, and I can get to C,